This week we begin looking at matrices as objects unto themselves. Instead of being associated with a system of equations, we say, okay, if we just have a matrix, this array of objects, what can we do with that matrix? And eventually that will come back around to working with systems of equations again. So just to remind you, the size of a matrix we always say is m by n. M's the rows, n is the columns, right? So we want to start thinking about if these are individual objects unto themselves, how can we deal with them? So one of the first things we would need is the idea of equality. So if you're going to tell me, for instance, that matrix A equals matrix B, how would I know that that's true? So I think one of the first things is obviously they should be the same size, right? So if this is true, they must be the same size. And further, I mean, you couldn't really say this matrix equals this matrix, right? That wouldn't really make sense. So if I was to just switch this, these are two different things completely. And so I would say these do not equal. And so if I want to say these don't equal, I would say because the entries are different, right? So really we would say they have the same size and the same entries. I think that's really logical, and it gives us a baseline saying, okay, you're going to treat matrices as their own objects. We need to know what it means when they equal. So I think it's a really straightforward definition. One way I could test this definition is by giving you a problem like this. And because this is really the only way to test that definition, I thought I'd talk about this problem. So we have two matrices set equal to each other, and we're supposed to find x such that this statement that they equal is true. If you look, every entry is the same. The only thing that looks like it might be different are these two. But when it says something like find x such that this is true, you say, well, the only way this is true is if these two entries equal. And so x minus 9 equals 16x plus 1. In other words, it's only true if 15x equals negative 10. In other words, x equals minus 10 over 15, which is really minus 2 over 3 if I divide both by 5, right? So in this case, then you could definitely say this is true. And so that's just a quick way to kind of test that you understand that. Now, if we understand what it means for two matrices to be equal, the question is, well, what else can you do with two matrices? Right now, like I said, we're not too worried about how it might be useful, but instead just practicing working with the matrices themselves. So, of course, you can add and subtract them. Both is done by working with the entries individually. So if I had these two matrices, A and B, the way that I would find the matrix A minus B is by subtracting entry by entry. So this would be 2 minus 1. 1, 9 minus 1, which is 8, minus 1 minus a negative 1, so 0, and 5 minus 0, which is 5. Notice that this itself is a matrix, and something very important, if you're going to do this, go entry by entry, obviously you're going to need these to be the same size, right? So this would be only defined if A and B are the same size. So if B had like another row here, if we extended B, then this would no longer be true over here, and actually A minus B would be undefined. And all you can really write down is undefined or does not exist. Sometimes people would write down. Again, I think this is also a very straightforward definition. I can add them in a similar way, and it just gives me the ability to work with matrices. Okay, so we have the idea of equality. We have the idea of addition and subtraction. Now, come into questions that you don't usually ask yourselves. Is this addition that we just defined entry by entry commutative? So what that means is, can you trust that A plus B equals B plus A for every matrix A and B that this is defined for? This is true, so yes. And it's all because you're working with individual entries, and those individual entries are numbers. And with numbers, you do in fact have the 1 plus 3 equals 3 plus 1. Okay, associative. So what that means is, can you say that the following is true? If I have three matrices that I'm adding, can I add these two first and then add that one? And is it the same as if I added the first two and then added the third? And this is actually true as well. This is again because the associative property holds for numbers. Okay, what if I ask you something like, can I undo this? So if I add A plus B and I get a new matrix C, can I somehow go back to A? And yeah, I can. I can essentially subtract the matrix B from both sides. In other words, you can work with this like you would with equations. So I can find A by finding C minus B. And finally, is there a matrix that acts like 0? So you have 0 plus 1 equals 1. 0 plus any number equals the original number. And yeah, we can actually talk about the 0 matrix. So if I'm dealing with 2 by 2 matrices, this matrix right here would act just like 0 with numbers. Now, I asked this about addition and subtraction, but when we talk about multiplication, a lot of this is no longer true. For instance, matrix multiplication is not commutative and only in special cases. And so we'll talk about this, and this is actually really important. And the question, can you undo matrix multiplication, is actually a complex one. It's actually in its own section, 2.6. Okay, now so for one last basic operation, we'll talk about scalar multiplication before we talk about matrix multiplication. Scalar would just be a constant, and so when you're multiplying it, every entry gets multiplied. So here 3a would equal 6, 27, negative 3, and 15, and negative 2b would equal negative 2, negative 2, positive 2, and 0, right? Again, this is just a basic operation, and you can see that it has a very logical definition. Here, it doesn't really make sense to talk about a times 3, so we can't really talk about commute and all that kind of stuff. This is the really the only way that you'll see it. All right, so what I want to really build up to in the main topic in this section that would be a little bit of work to understand would be matrix multiplication. So the first thing I want to do is talk about the dot product, and the dot product is a way of multiplying two matrices of very specific sizes. So this, as you can see, has one row, it has n columns. And so this is a 1 by n matrix, whereas this has n rows and 1 column, so this is n by 1. And what you end up with is a 1 by 1, in other words, just a number. This is actually a scalar. So the dot product is a way of taking two matrices of a specific size, so basically a row times a column, and you end up with a number. And what you're doing is you're multiplying this entry times this entry, plus this entry times this entry, and so on. We're going to practice this first and then use this to develop a product for general matrices. So looking at this, remember to pay attention to the sizes of the matrices you're working with. For example, this is a 1 by 3, and this is a 3 by 1. These two inner numbers have to match or this will not be defined. And we'll talk about that in a little bit, more in a little bit. So this is always a row times a column. And that makes sense because think about it, we always work with the idea of rows and columns. So the way I would find this is I'd say, okay, 2 times negative 5 first entries multiplied together, plus negative 3 times 2, plus 0 times negative 2. So I end up with negative 10, minus 6, and then 0, so I get negative 16. Right? So let's just go through one more time. Dot product here would be minus 2, 0, because 0 times 3, 3 times 4, so this 3 times 4, so it would be plus 12, and then minus 4. So I actually, if you look at this, I actually have minus 6 plus 12, so I end up with 6. Again, it's really just an algorithm, and you just have to get used to applying it. You just have to memorize this procedure. And here this was defined because it's a 1 by 4, and this is a 4 by 1, which I glanced at, but I didn't state. And so I want to point that out. These two inner numbers have to match up for this to be defined. All right, so how would this apply to multiplying two larger matrices? Well, what we'll do, and I think this is a complex, this is the exact definition, but what you can imagine is we're going to take a matrix, and so here will be my first matrix A, and let's say that has 3 entries in this first row. And we're going to take a matrix B, and it needs to have 3 entries in the first column, and 3 entries in the next column. It has to have the same number of entries as we have over here for the row. I'm going to take this, and I'm going to do dot product here, and dot product here. And that'll give me my first 3 entries in the product A times B. Then I'm going to take the next row and do the same thing. So the way I think about this is rows hit columns. And you fill up across. So if I want to multiply A times B, I'm going to take the rows of A and I'm going to hit the columns of B. And then my result will have the answers for those dot products. Now this is only defined in certain cases. So matrix A, let's say is m by n, and matrix B we'll say is n by p. You have to have these two numbers They must match, otherwise it's undefined. Okay, so this is defined only when the inner numbers match. So what are those inner numbers? This is, remember, rows, columns. So the columns of A, so the number of columns of A has to match the number of rows in B. And so what is going to be the result? Well, the result will be from these numbers here. So the result will be a different size matrix. It will be an M by P matrix. So this is an expansion of the dot product into dealing with these. And remember, it's not necessarily commutative. So A times B does not necessarily equal B times A. In fact, it might not even be defined. This is one of those things you really have to see to understand, in my opinion. So I can sit here and talk about it all day, but really you need to see it in action. So here's 3 examples, and we'll go through each of these talking about the steps we need to find these products. All right, so let's check the sizes first, because if it isn't defined, I want to know it. This right here is a 2 by 2 matrix, and this right here is a 2 by 3 matrix. Okay, these 2 inner numbers match, so I know this is defined, and additionally, I know the answer will be 2 by 3, so answer will be 2 by 3. All right, so when I do this, I'm going to take, starting out, I'm going to take this row, and I'm going to do a dot product on the first column, the second column, and the third column, and that's how I'm going to get my first 3 entries across in my product. So when I do this, again, I'm going to use that rule we just saw. So I'm going to have 1 times negative 1. So 1 times negative 1, I'll write it out this time, plus 3 times 6. So that first entry was me taking that first row and doing the dot product with the first column. Now I'm going to take this first row and do a dot product with the next column. So I'm going to get 1 times 2 plus 3 times 7. And now I'm going to do a dot product with this. So I did it with this, did it with this. Now I'm going to do it with this one. Get 1 times 0 plus 3 times 8. Now, yeah, your calculator will do these products. It's a little bit of a pain to do them, but you must know how to do them by hand, because we'll be working with variables in products soon, and your calculator can't do that. So sometimes people get a little discouraged because it takes a little bit to get used to the mechanics. But as you can see, it's just repeated dot products. All right, so that first, everything in the first row came from this first row, right? So now what I want to do is use this second row. Use the second row and do the dot product here, here, and here. So first here. That'll give me my first entry, so that'll be 5 times negative 1 plus 4 times 6. My next entry is going to be from here, 5 times 2 plus 4 times 7. And then my final entry will be from here, the dot product with this, and it'll be 5 times 0 plus 4 times 8. After all that work, which in the end, notice all we did was multiply numbers and add them. That's what we're about to do. We just need to simplify. So it feels like a lot of work, but really what you're doing are simple operations applied over and over again. So my entry here, this is going to be minus 1 plus 18, so I guess 17. Okay, 2 plus 21. Nothing plus 24. Negative 5 and 24. 10 and 28, and 32. So there's the product A, B. So 2 things to comment on here. That's the product A, B, like I said. And then notice that BA, if this was matrix A, this was B, would be undefined, because that would be a 2 by 3 times a 2 by 2. So in this case, not only is BA different, it's actually undefined completely. Okay, let's look at a second one. Let's see, this is a 2 by 4, and this is a 3 by 2, and this is done. These 2 inner numbers do not match, so this is undefined. And so I think the online homework has you writing DNE, but what they have you doing is you have to actually put DNE in every cell, every space where there's supposed to be a number, put DNE, and then they will accept that answer. So this is undefined because those 2 inner numbers don't match. All right, this last one looks almost like a reverse dot product, right? So if I look at this, I see here that I have 3 by 1, and I have a 1 by 3. Okay, the inner numbers match. What am I going to end up with, though? A 3 by 3. That's really interesting. How is that going to happen? Well, our rows and columns are single numbers. So when I use the first row times the first column, it's just -5 times 2. Now the first row and do the product with the second column, it's just -5 times -3, it's 15. And -5 times 0 gives me that last entry, it's 0. So you can see that it's still the same idea, but it's much simpler. And now I'm going to use this particular row, hit every column, and then do the same thing again. So I get 4, -6, 0, and then I get -4, +6, and 0. So there's my product right here. And we already know that if this is A times B, B times A is defined, but it's actually a single number. So matrix multiplication behaves much differently than we would expect. And so I think that as you work through these problems, you should, of course, practice a whole lot till you're comfortable with the algorithm. But as you work through, pay attention to ask yourself, okay, would B times A be defined or would it be undefined? How different would it be if it is defined?